Today in this demo, we will present the first demonstration of the AI-RAN blueprint for studying and evaluating AI-RAN coexistence. This demonstration is the result of a project within Working Group 2 and led by zTouch Networks in collaboration with Northeastern University and Red Hat. The blueprint provides a platform for programmatically and automatically benchmarking and testing AI-RAN workload coexistence. It addresses the main challenges in AI-RAN coexistence, such as identifying optimal GPU sharing policies, and determining optimal GPU partitioning strategies using multi-instance GPU or MIG. The platform also allows to profile AI-RAN workloads and characterize their performance when the physical compute and networking infrastructure is shared. In this way, the platform provides a simple and easy way to reconfigure the physical infrastructure, deploy workloads using different GPU sharing policies, and monitor their performance to identify the boundaries of AI-RAN coexistence. The platform also supports the study of secure AI-RAN sharing to identify good practices for ensuring isolation across workloads and guarantee privacy and security. This is an overview of the hardware and software infrastructure you will see today in our demo. The physical infrastructure consists of a GB dev kit server equipped with an NVIDIA A100 GPU partitioned using MIG. AI-RAN orchestration is provided via our zTouch OS platform that offers automation, orchestration, monitoring, and GPU sharing management capabilities. RedHat OpenShift provides reliable and efficient container management. The demonstration includes a commercial radio unit, preloaded AI training and inference tasks, as well as RAN workloads such as GPU-accelerated RAN functions, such as OpenAir Interface and NVIDIA Arc. The blueprint includes a dashboard to monitor infrastructure utilization, as well as resource computation for each MIG partition and AI-RAN workload. It allows to deploy, monitor, and select GPU sharing policies for each AI-RAN workload and reconfiguring GPU sharing policies in real time. In more detail, the dashboard provides information on active MIG partitions and available resources. You can also track AI-RAN workload execution over time and monitor GPU utilization for each MIG partition to identify bottlenecks. It is also possible to monitor individual workloads and keep track of memory, bandwidth, and CPU utilization over time. The dashboard also provides a log toolbox for tracking AI-RAN workload execution. This can also be used to determine deployment status and time, monitor AI metrics such as inference and training steps per epoch, as well as RAN metrics such as throughput and latency. You can easily identify active GPU sharing policies, visualize sharing policies supported by the specific GPU model available on the node, and select new policies in real time. The activation of a new MIG profile takes around 30 seconds, which is necessary to reconfigure the GPU, reallocate, and reinstantiate the AI-RAN workloads. More importantly, the dashboard provides flexible AI-RAN workload deployment tools. You can deploy workloads hosted on public and private repositories, select which MIG partition should be used and the desired GPU sharing policy. Our AI-RAN orchestrator zTouch OS automatically handles configuration and deployment of the workloads. Once you deploy workloads for the first time, you can store the configuration, which zTouch OS saves and converts into a template that can be used for future deployments. Once deployed, you can use the dashboard to keep track of deployment times and workload execution. This feature allows you to streamline AI-RAN workload deployment and test different GPU sharing policies to identify feasibility regions and minimum resource requirements for each workload. This feature makes it possible to perform a set of automated tests whose logs are used to generate detailed reports that help AI-RAN members in designing and selecting optimal GPU sharing policies to ensure effective AI-RAN coexistence. In this case, we have deployed a training task for a ResNet model as well as a GPU-accelerated 5G base station running NVIDIA Arc and OpenAir Interface. The dashboard shows that the two workloads coexist on the same infrastructure and can share the same GPU while utilizing different MIG partitions to ensure isolation. Once the workloads are deployed, you can monitor GPU and CPU utilization over time for each workload and identify how GPU sharing impacts infrastructure utilization. In this demo, we have presented the first AI-RAN blueprint that will help AI-RAN Alliance members to execute automated tests, understand AI-RAN coexistence, and develop the next generation of AI-RAN systems. Thanks for your attention.